Hello everyone, my name is Pauline Dredger and I'm here to talk to you about the work I've been doing regarding the rotation of the Y component of the magnetic field out in space across the magnetopause. So first of all, what is the magnetopause? The magnetopause is the boundary between the solar wind and the Earth's magnetic field. Now the solar wind carries interplanetary magnetic field, or IMF, and plasma. And so once it hits the Earth's magnetic field, it piles up in this region, the solar wind piles up in this region called the magnetosheath. So we have compressed magnetic field and compressed plasma, and this is a very turbulent region. Now, because the magnetic field in the magnetosheath is different from the magnetic field inside the magnetosphere, according to Ampere's law, we get a current flowing on the shock, or on the magnetosheath. And so we want to characterize this current and because it's a three-dimensional current density, in fact. So first of all, how are we going to locate this magnetopause and how are we going to take these measurements? Well, via satellites, and we have the Themis satellites, which are on an elliptical orbit such that they can will be in a region in that they can measure the magnetopause at times, depending on where it is. It's drawn in nominally here, according to some models, but we don't know where exactly it will be. It depends on solar wind conditions. And so a word about coordinates. In this study, we use GSM coordinates, which roughly means that the X is towards the sun, Z is out of the North Pole, and Y is in the equatorial plane. So this upper frame is in the X Y plane. You see the orbit of the three Themis satellites, and then this is the XZ plane, and this is the YZ plane. And these satellites can measure magnetic field. They can also measure plasma parameters. So what do these measurements tell us? Well, because the plasma parameters and the magnetic field are very different in the magnetosheath versus the magnetosphere, if the satellites are reading a sudden change in magnetic field or in plasma parameters, we identified this as the boundary between the two regions, or the magnetopause, as shown in this in these plots. And so this is a way to identify the current, because the current is due to the change in magnetic field. And these are two cartoons of the Z component, examples of the rotation of the Z component from up here in the magnetosphere values, where it's strongly positive, down to magnetosheath values, where it can be negative if the solar wind magnetic field IMF is negative. So we have two examples of crossings. We have a northward crossing here, and when we have a northward crossing, we identify the magnetopause by looking at the plasma parameters, and we put the magnetopause here in red. This is the time when the satellite, we say, encountered the magnetopause. This is when the plasma density suddenly decreases down to a low density, which is more indicative of magnetosphere values, because there's much less plasma in the magnetosphere than in the magnetosheath. This is the plasma pressure. Follows a similar pattern. Then we look at the magnetic field. We see that as the satellite goes from the turbulent magnetic field, where we have a lot of ups and downs here, to a smooth magnetic field up here in the magnetosphere. And we see that the Y and the Z components of the magnetic field are both rotating in the same place. So they're both giving a current on the inside of the magnetosphere, or excuse me, of the magnetopause. And we see in this scatter plot that they're rotating together. With this southward crossing, we have some rotation of the Z component on the exterior of the boundary as well as in the interior, but the BY component only seems to be rotating inside, and this is backed up by this scatter plot. We see there is a correlation between BY and BZ on the inside, but not on the outside. And so because of this, we conclude that there is no exterior current on the magnetopause due to BY, although there is some due to BZ.